Suppose we have a particle that moves along a curved path in a gravitational field. Then the work done by the gravitational force as the particle moves an infinitesimal distance along the path ds is the dot product between a gravitational force and a displacement vector. And we can write this dot product in scalar form if we resolve the displacement vector along the radial and theta directions. So the gravitational force only does negative work in the radial direction, which we can rewrite as follows. And now we can integrate from R1 to R2. So now if we substitute for the gravitational force, and that change in gravitational potential energy is equal to the negative of the work done by the gravitational force. And now evaluating this integral gives the following expression. For the change in gravitational potential energy. So for example, if R2 is greater than R1, then we get a negative result in a bracket, and therefore a positive change in potential energy, as the particle is doing work against the gravitational field to get to that position. And given that the force of gravity is a conservative force, then the change in potential energy only depends on the endpoints and not the path the particle takes. We derived an equation for the change in potential energy as a particle is displaced from position 1 to position 2 along a curved path. Now suppose the particle is displaced from position 1 to a position of infinity. Then we rewrite the change in potential energy as follows, and we call this R. So as R approaches infinity, this term goes to 0, and we choose our reference potential energy at infinity to be 0, which gives the following expression. Or more generally, we just remove the 1. So given that the potential energy is always negative, this means that energy must be added to displace a particle that's at a distance r from an object producing a gravitational field to infinity, because an external agent would be doing work against the gravitational field to achieve this. The kinetic energy of a satellite in a circular orbit can be written as 1/2 by the mass of the satellite by the speed of the satellite squared. And you can also write this using the angular speed and the moment of inertia, which gives you the same result, because the speed is related to the angular speed as follows. Now using Newton's second law, the gravitational force provides a centripetal acceleration, and doing some cancellations, we can write the speed of the satellite as follows. And if we substitute this in the kinetic energy expression, we can write the kinetic energy of the orbit as follows. So given the speed of the satellite is inversely proportional to the square root of the radius of the orbit, then it makes sense that the kinetic energy is inversely proportional to the radius of the orbit. The total mechanical energy of a satellite orbit around the Earth is the sum of the kinetic energy and the potential energy. And we derive the kinetic energy as follows. And using our reference point at infinity, the potential energy can also be written as follows. So therefore the total mechanical energy of the orbit can be written as follows, and is inversely proportional to the radius of the orbit, and it's equal to 1/2 of the potential energy, and always less than 0. We can find the escape speed of a rocket fired from the surface of the Earth using the conservation of energy, which is the minimum speed required to escape the gravitational field. And in an ideal non-orbiting case like this, we can apply the conservation of mechanical energy, where the sum of the initial kinetic and potential energies is equal to the final mechanical energy. So because we want to find the escape speed, which is the minimum speed to escape the gravitational field, then we set the speed at infinity to be 0, and therefore the final kinetic energy is 0. And we also took our reference potential energy at infinity to be 0. So therefore, the kinetic energy can be written as follows, and the potential energy as follows. And now we can solve for the escape speed. A ball is dropped in a frictionless tunnel, which is dug below the surface of the Earth. Derive the change in gravitational potential energy as the ball moves from A to B. Well, the work done by the gravitational force is equal to the negative of the integral of the force over the radius. And we assume R1 is less than R2, so the gravitational force does negative work. And given that the ball's below the surface of the Earth, the gravitational force varies linearly, as we've derived previously. And if you evaluate this integral, you'll obtain the following expression. And the change in gravitational potential energy is the negative of the work done by the gravitational force. And in our case here, the ball starts from the radius of the Earth and ends up at B, which is at a distance r from the center. Now part B asks us to derive an equation for the speed of the ball as a function of r from the center of the Earth. We're using the conservation of energy between points A and B. So from this expression, we have the negative of the change in gravitational potential energy, which is UA minus UB, and that's equal to the change in kinetic energy. And because the ball's dropped from rest, the change in kinetic energy is 1/2 mv squared. Then you can substitute this expression and solve for V. And I'll leave it for you to do part C. We are asked to find the point where the speed of the ball is at a maximum.